Yeah, welcome back to the Quantitative Methods in Mathematics 1. My name is Dr. Simon Nick, and today we are going to look at the complex numbers, and specifically we want to look at the Euler representation. The last time we introduced the complex numbers, so we basically said what is I square is minus 1, and we showed also that we have some right I, which is basically nothing more than the square root of a plus b square, and we showed that a complex number has a real part plus some imaginary part. Okay, and our alternative goal, why we want to present this in this Euler representation, which is basically nothing more than some radii r times e to the power phi I, and this phi is just an angle, okay? And our ultimate goal is that we have like a complex number is written as 1 plus I divided by the square root of 2, and we want to take it to a power like 255, and let's see, okay, this is too hard to determine this here by hand, so we want to take care of the Euler representation so we can show how easily it can be calculated. Okay, anyways, let's start with the imaginary numbers. Let's look what we got here. So I already wrote something on the table. So we have on the y-axis, we have the imaginary numbers. On the x-axis, we have the real numbers. What we know, we assume for a moment that our radius is just 1. So this means here we start at 1. And since we know, I will talk about these angles in a bit, but from now we just assume it's 1. Then we say that we have a complex number z, a plus b, bi. So we can say this part, the imaginary part, is b, or real part is a, and we have some angle a, some angle phi. Okay, and how can we now represent these a and b with this angle? It's quite easy. If we start with the cosine of phi, we know the cosine of phi is basically the adjacent side divided by the hypotenuse, a divided by r, because we have here a right angle. We have, in German we say right angle, here it's a 90-degree angle, so we can use the Pythagorean theorem. Okay, so this is this representation. We can rewrite this as r times the cosine of phi is equals to a. In a similar fashion, we can say the sine of phi is nothing more than b divided by r. Okay, and we can write it as r times sine of phi, and this is equal to b. And now we look at the complex number z, which is a plus bi, and this can be written as, now we substitute our a, this is r times cosine of phi plus I, and our b is the r times the sine of phi. We can take r out here, and we have this representation. This is nothing more than e to the power of phi I. Okay, and now we're talking about the angles. We know this representation, from this representation, we know that we are concerned basically with a cosine and a sine. And we know that both of these functions are 2 pi periodic. That means if we start at some value 1, it takes 1 period, which is 2 pi, to end up again at 1, for example. Okay, this means, let's say we start at 1 here, then this is 1, so 2 pi, we end it here. If we go quarter of this angle, we see we end up here. This is pi divided by 2 pi halves, which is equal to the imaginary number I. If we go even further, we end up, this is basically 90 degrees, okay? And when we end up at the point minus 1 is here nothing more than pi, or 180 degrees, and 270 degrees, I guess you already understand, right? We end up by minus I, 3 halves of pi, and then a full circle is 2 pi, okay? So this is what we basically get. And other representation here could also be, if you don't want to really focus on how you can derive this part by part, you can also say, okay, we don't need the sine, we don't need the cosine. We can take the arctangents of phi, which is directly b divided by a, and then yeah, this is basically what you get for the angle. Okay, this is also possible. What I really like to do is I always like to write it in this representation, so I can see, okay, where it really comes from. Okay, and another way where you can see, you don't have to always try to use usually people tend to take the calculator for this calculation, but you don't really need to, because if you have like this table with some common degrees, okay, we can see it either in radian or in degree as we know it. Okay, you need this table and you're basically set. You can know how to read it. We will in a moment see how this works out. Okay, now let's go to my question. To what we are really looking for is we want to solve this equation basically, right? We want to solve 1 plus I divided by the square root of 2 to the 255 power. Okay, this is hard to get, but it's unimaginable how we can solve this, but we will see in a moment. It's quite easy. Okay, let's just look in the inside and rewrite the complex number. Okay, we can write it as follows. And we know that this one is equals to this because 2 is equal to square root of 2 times square root of 2. Okay, and what we can see here, we see both are positive. This means we are exactly here, right? So the angle is 45 degrees or 4 pi fourth. This means we can represent this. We can represent this complex number as follows. Okay, so the real question now is, what is this times 255? Okay, we can start first. We just multiply it, so we have 255 divided by 4 pi I. Okay, this is, I think, this should be nothing too special, and then we can rewrite it in a little bit different way. Okay, what we can write is it's E63 pi I. So, but what's really left over is we can write it as follows. Okay, now what we can see is this can be further decomposed as E 2 pi I times 31 plus pi I plus 3/4 pi I. Okay, why did I write it in the following sequence? This is important because we know 2 pi is basically 1. This means what we write here, we have 2 pi I times 31 times E pi I times 3/4 pi. We know this is equal to -1, as we can see here. And this is equals to 1. So what we have here is -1 times and 3/4 of this. Here we get for the cosine write it as follows, and this is equal to I. So basically what we get is, so we took the complex number to the 255 power, and the only thing that changes is that the sign for the complex part of the for the imaginary part of the complex number switched. Okay, yeah, quite interesting, right? Okay, see you next week.